Hello and welcome to DagsHub walkthrough session. My name is Nir Barazida. I'm leading the data science advocacy and outreach activity of DagsHub worldwide. The main purpose of our session today is to get to know DagsHub in an interactive and basically fun way. We'll explore the main features and tool integration that DagsHub has to offer and gain hands-on experience using those tools with DagsHub. I would just note before I'm going to start the session that if you have any questions regarding what I'm going to cover in this video today, please feel free to reach out on our Discord channel. You have the link to the Discord channel in the video description below, or you can leave a comment to this video and I'll make sure to provide you with all the answers that you need. So we're in for a fun ride, so let's get this show on the road. We'll start as always with our agenda for this session. We'll start by exploring DagsHub to better understand how it can help us to manage our project more efficiently while having all of its components under one roof. We'll use Dean's project, SavtaDepth, as a case study and explore how DagsHub helped him to pinpoint why his model is performing badly and what he needs to do to improve it. We'll then learn how to track our ML experiments, save them to DagsHub servers, and visualize them under the Experiment tab using MLflow and Git. We'll have an interactive session where we'll showcase you how to track your experiments using MLflow to DagsHub remote tracking server and see them in your first ever DagsHub repository. Next, we'll explore the usage of DVC for tracking large files and host them on DagsHub Storage to be accessible to all of the project's collaborators. We'll have an interactive session where you'll be able to follow my lead to configure your local machine with a remote DVC storage to track your very first file using DVC and push it to your DagsHub storage. So, I hope you packed your bags because we're going on a trip in the DagsHub land. So, this is DagsHub. As you can immediately see, the UI is very similar to GitHub, and this is something that we're aimed for. We don't want to reinvent the wheel wherever it's not necessary. We want to make you feel as comfortable as possible. However, on top of the Git features, we spiced it up with some data science capabilities. And behind the scenes, the repository that you see here is connected not only to a Git server, but also to a remote storage with 10 GB of free storage, and a remote tracking server to log your experiments information. You can see all the servers URL here under the remote button. You have the Git remote, the DVC remote, and the MLflow tracking remote. And if you want the commands that will help you to configure your local machine with those remote servers, you can see them under the question mark here. So, before we're going to dive deeper into the details of what DagsHub is, let's first understand what this project is trying to achieve. So this project was created by Dean, our CEO, where he's trying to turn 2D images into 3D by predicting the depth dimension. And just for the jigs of it, let's see a 2D image with its corresponding depth image. So if I'm going to go to the source code, and this is something that is very cool with DagsHub, that you have everything under one roof. So all the data files that we're going to see now, all the images that you're going to see now, they are hosted on a remote storage, but we're able to see them and visualize them in DagsHub UI. So I'm going to go to the data, the raw data, and I'm going to see my 2D image. Let's choose the bathroom. And this is the depth image. And as you can see, the depth image is black and white image where the pixels are lighter for objects that are far from the camera and darker for closer objects. So now that you understand at a very high level what is going on in this project and how the dataset looks like, let's go back to the repos homepage. And the first thing that pops up here is the pipeline visualization. And this is a DVC pipeline that DagsHub lets you to interact with, and it can help us to onboard the project and understand what the heck is going on here and how the different components interact with each other. So as you can see, DagsHub shows us the different stages of the project and what files are used in each step, aka the dependency files, and what files are the output of the stage. Moreover, you can easily see what tool is tracking the different files and access them in a click of a button. So it doesn't matter if it's being tracked by DVC or by Git, you can still see them in DagsHub UI, even if it's being hosted on a remote storage or in a remote Git server. And this pipeline visualization is very useful when you're trying to onboard to the project and figure out what is going on here. And not just that, the DVC pipeline provides us the ability to run all the updated stages with a single command. So for example, let's say that we didn't updated the processing step, but we updated the hyperparameters of the model. So DVC will know that nothing was updated in the previous stage of the data processing, and it will start running the pipeline from the modeling step. It will skip the processing step. And this is a very powerful capability when we have a long pipeline that takes a lot of time to run, or it consumes a lot of resources. And scrolling back up to to see the project files, this is a very familiar look. It's very similar to what we have on GitHub, but you can see the smart tabs that we have here, which let us filter between the different types of the files in the project. So we have the data files, and as you can see, the files that are being tracked here by DVC has a bluish background with the DVC logo instead of the Git commit. We have the models that we can filter and pinpoint easily. We have the different notebooks, and we can filter all the DVC tracked files and the Git tracked files. And on the top tab bar, we can spot the files, the issues, the pull request, and the wiki, which is once again very similar to the GitHub UI. But we have something strange here, the experiments. And under the experiment tab, we have all the experiment that we logged in this project by both Git and MLflow. And we can filter, sort, label, and basically do whatever we want to easily see which experiment provided the best results. So as you can see, we have the source, which is either Git or MLflow. We have the commit, the relevant commit. We have the label. We have the parameters with a bluish background here. And we have the metrics that we logged in a pink background. So I'm taking you back to Dean's project. And during his work, he created 3 experiments. And in each experiment, he had an identical parameters, but he changed the training time of the model. So we use different epochs, 1, 10, and 50. And we all would assume that the more epochs that you train the model, the better result is going to provide. So if I'm going to filter now back to the experiment that he was using when he had this, I will give you a spoiler, a bug. So he committed them all to DagsHub and used the comparison tool to check the different results. And how did he do that? He simply clicked on the 3 experiments and clicked on the compare button. And as you can see here, Dean now have all the 3 experiments in a side-by-side presentation. So we have the metadata about the experiment, who is the author, when was it committed, what is the git commit hash, when was it created, etc. We have the different parameters of the experiment, and we have the metrics. On the middle, we have the parallel coordinate plot that can help us compare not only between one parameter or metrics, but using multiple parameters and metrics. And on the bottom, we have the bar chart. And for Dean, he was using as relevant metrics the A1, A2, and A3, and the epochs. So I'm gonna only keep in the parallel coordinate plot the epochs, the A1, A2, and A3. Let's change the order here a bit. So A1, A2, A3, and the number of epochs. And basically, Dean tried to minimize the number of epochs and maximize the number of A1, A2, and A3 results. And as using the parallel coordinate plot, we can easily see that something is weird here. What do I mean by that? We can see that as we're having the lowest amount of epochs, we're getting the better A1, A2, and A3 results. And this is very weird. So Dean couldn't figure out what is going on here. So we decided to retrain the model one more time for 50 epochs, but this time he plotted the output of the model, the prediction of the model, to an eval directory. And if I'm going to go back to the 50 epochs commit, which is very easy to do with clicking on a button. So if I'm going to go to the model predictions, we can immediately notice that the model is doing a great job, but just the opposite of what it should do. So the model used lighter pixel for closer objects and darker for further objects. And at this point, Dean simply reversed the optimization process of the model, and voila, the model produces state-of-the-art results. So to compare the result, all Dean had to do is use DagsHub comparison tool. So if I'm going to go back to the main repository, and I'm going to click on the epoch testing fixed and compare it to the epoch testing, we can first see that DagsHub let us not only to compare between files, but also to compare different directories. So we have here the files or the directories with white background that weren't modified. We have the directory with yellow background that were modified. And if something were deleted or created, it will have either a red background or a green background. So I'm going to go to the source, to the eval and the examples. I'm going to click on one of the predictions, and I'm going to immediately see the difference between the model predictions. And once again, this is something very powerful for us because first we have all our data at the same place as our code files, and we can access it in a single or the same UI. And by using the comparison tool, we can easily view the files side by side or in an easy to consume way that can provide us valuable insights. So this basically leads me to one of the most, I think, valuable capability that DagsHub has, which is the ability to diff practically anything. Well, not really, but a lot of different types of files, from open formats such as CSV and JSON files to Jupyter notebooks, which I think this is one of the most powerful capabilities, the diffing capability that DagsHub provides, to all standard images files, and even 3D MRI scans. And hopefully we'll add more capabilities as we go along for audio diffing, for more medical images, and more. By the way, if you have any requests for more file type diffing capabilities that you want to have on DagsHub or present them, you can reach out on our Discord channel or leave a comment in this video, and we'll make sure to add it to our prioritization. So if I'm going to choose here either a branch or a git commit, I will be able to compare between the different files. And I would want to first start by comparing Jupyter notebooks. So I'm going to go back to the source code. Under the code directory, I have here the notebook that Dean used. And if I'm going to click on it, we can see the cells of the notebook that were either added or modified. And it will have, once again, either a white background if they wasn't modified, a green background if they were added, or a red or yellow if they were deleted or modified. And once again, this is very powerful because Jupyter Notebooks is a very strong tool that a lot of data scientists are using for their research. And this is something that we really can use and be powerful for us. Secondly, we'll have the CSV diffing. And as you can notice here, first of all, the CSV file is being shown in a table that you can easily filter, and it's not in its raw format. And the rows and columns that were modified are marked in a yellow background with the old and new value, and the rows or columns that were dropped are marked with a red background. And once again, this provides us with a lot of information that we can drive insights from. So by that, we covered the main features and tool integration that DagsHub has to offer. We definitely didn't cover all the features that DagsHub has. There is the data science pull request that lets you merge not only code files, but also data files. There's a ton of different experiment tracking capabilities. There's a lot of different features that we obviously can cover in one walkthrough session. So I highly recommend going back to the platform, taking just like a project that you think that is very valuable, that has data set, it has models, it has pipelines, it has experiment, fork it to your profile and start exploring it, seeing the different files, exploring the different features, checking out the pull request and all the data science capability that we spiced it up with. And I think that by that, we can continue on to the next part of the session, which is the experiment tracking. Now that we got to know DagsHub and its capabilities and how it can improve our workflow, I'd like to dive into the practical part of this session. And in this part, we'll explore the DagsHub experiment tracking capabilities and tool integrations. DagsHub supports two experiment tracking tools to log the experiment information and view it under the experiment tab. The first tool is Git tracking, which is unique to DagsHub. By logging the information to open formats such as CSV and JSON files, commit them to Git, and push them to DagsHub, it will log the information and present it in a meaningful way under the experiment tab. The other option is using MLflow tracking that provides us the ability to log the information not only to a local database, but also to a remote tracking server, which DagsHub provides you and automatically connects with your remote repository by simply adding a few lines of code to your Python script. We'll start by covering the Git tracking integration. So Git is an open source tool for tracking changes in any set of files, usually used for coordinating work among programmers in software development projects. Its goal is to include speed, data integrity, and support for distributed and nonlinear workflows. And we know that many data scientist teams are adopting Git to their workflow, which I think is really great and very useful. And therefore, we decided to support it as an experiment tracking tool. So how does it really work? It sounds very intimidating or weird, I know, but I promise you that it's extremely simple. So all you need to do is log your experiment information to open format files that end with either params.yaml for parameters and metrics.csv for metrics, and track them using Git and push them to DagsHub. DagsHub will parse the Git commit for those special files with those special names. And if it finds a new file or an updated file, it will create a new experiment. And the main advantage of logging experiment using Git, and if you're also using DVC to track your large files, your data files, so your data models, pipelines, etc., you can encapsulate the information of the experiment with all the other project components and then easily reproduce the experiment result by simply running the git checkout command. And to help you do exactly that, we created the DagsHub Logger. And what is the DagsHub Logger? So basically, the DagsHub Logger is a simple Python logger that we created additional method on top of it to log your information to those special files, which are not that special, they only have a special name. And you can either use it as a context manager and log your metrics and your parameter either as a single parameters or in a dictionary format, or you can use it as a normal Python object, but just make sure that you're saving it and closing it. And once you're going to run your Python script with this code that I just showed you here, it will output those files and it's going to name them metrics.csv and params.yaml. All you need to do next is track them with Git, commit them, and push them to your Git server on DagsHub, and a new experiment will be generated. The next tool that DagsHub supports for logging experiments is MLflow. MLflow is an open source tool for managing the end-to-end machine learning lifecycle. It tackles 4 primary functions, which are MLflow tracking, MLflow projects, models, and model registry. Today we will be focusing on MLflow tracking, which is an API for live logging of parameters, metrics, and metadata when running a machine learning code. MLflow provides us the ability to either log the experiment to our local machine or the machine that we're running the experiments on, or to a remote tracking server, which will make the experiment visible and accessible to our colleague outside the machine that we're running the experiment on. All we need to do is add a few lines of code to our Python script, set a tracking server we want to log the experiment to. It can be either locally or our remote tracking server, and run the script to create a new experiment. This is a very useful capability, first to track the different experiments that we are running, but also to see the training process while it's running and see if the process or the training is converging or not, and stop it in the middle if necessary. If you're working in a team using more than one machine to run the experiments, or your training process is consuming a lot of resources, you'll probably want to log the experiment to a remote tracking server. But this is where the MLflow's bar is getting a bit higher. To set a remote tracking server and configure it with your machine that you're running the experiment on can be a bit of a hassle. And this is where DagsHub comes to the rescue. To support the core data science capability while doing the MLOps heavy lifting for you, we decided to also support live logging of experiment and automatically configure a remote MLflow tracking server for every new repository that you create on DagsHub, and integrate it seamlessly with the experiment tab. You can find the remote tracking server URL under the remote button. Here you have the remote tracking URI, and under the question mark you can see all the commands that you need to run to configure the machine with the remote tracking server. When you log an experiment using MLflow, you will see it in the experiment tab, where the source of the experiment will be marked as MLflow, the parameters will be shown with light blue background, and the metrics with a pink background. The experiment result will be shown in a graph while the experiment is still running, and the graph will be updated. All you need to do is refresh the page and the information and the graph will be updated. I think I spoke quite a lot so far, and it's time for some actions. So moving to the interactive session of the experiment tracking part, you will have the ability to follow my lead to create your very first MLflow experiments on DagsHub. You have all the links to the materials that I'm going to use in the video description below. You have a link to the Google Colab and a Notion page with all the Python code that I'm going to add to create the MLflow experiment. So we're going to start by going to DagsHub, and we're going to create a new repository. So I'm going to click on the create, a new repository. I'm going to name it MLflow demo, and I'm going to add a git ignore for Python. I'm going to create the repository. And as I said, once I'm going to create a repository on DagsHub, I'm going to have 3 remotes that are automatically configured with this repository. So if I'm going to click on the remote, I'm going to see them. I have the Git remote, I have the DVC remote, and I have the MLflow tracking remote. And now let's move to the Google Colab and see what is the project that we have here. So a bit of a high-level explanation of what is going on in this project. In this project, we're trying to build a model and train it to identify or classify digits in handwritten images. So the model is going to be fed with the good old-fashioned MNIST dataset, and we're going to try to predict the digits in the images. So I'm going to start by importing the MNIST dataset from TensorFlow datasets. I'm going to split it to train and test. Then I'm going to create a baseline model using TensorFlow models. I'm going to compile the model, and then I'm going to simply fit it. And I think this is a high-level explanation of what is going on here. This is a very simple project that will help us to add a few lines of code to it and create a new MLflow experiment. So I'm going to start by installing MLflow on my virtual environment. So I'm going to copy those 2 lines of code to here. And by that, I'm going to install MLflow, and then I'm going to import it to my runtime. Next, I will need to set the MLflow environment variables to provide access to the DagsHub remote tracking server from this remote machine. And how can I do it? So I'm going to copy those 3 lines of commands. The first one is setting the username. The second one is setting the password to DagsHub. And the third one is setting the remote tracking URI. And how can I get the remote tracking URI? So the username is the DagsHub username. The second, the password is DagsHub password. And the third variable here, we're going to go back to the DagsHub repository, click on the remote, and copy the MLflow tracking remote URI and paste it as a text in the remote tracking URI. And by that, we configured the remote machine with a remote tracking server. So basically, you can treat Google Colab as a remote machine, as an EC2 instance, even on AWS, that you need to configure with the remote tracking server. And by running those 3 commands, you're granting access to that machine to log the experiment information to the DagsHub tracking server. Next, I would want to add the code that would log the information to the remote tracking server. And if you're using a well-known framework such as TensorFlow that I'm working with here, or PyTorch Lightning, FastAI, Scikit-learn, or any popular framework, MLflow probably got you covered by implementing an auto-logging method. And what is this method? The auto-logging method will automatically log all the relevant parameters and metrics while the training process is running. And you don't need to manually log anything. However, if you feel like logging additional parameters or metrics, you can simply log them using the logParam and logMetrics methods. So I'm going to add those 2 commands here. And as you can see, the first one is MLflow.TensorFlow, and then the auto logging. And the second command is for logging my parameters. So I can log the task will be the parameter, and 2 will be its value. And now, all I need to do is to start the experiment, is to run the training process. And if I'm going to go back to my repository, I'm going to refresh the page. I will see that the experiment tab has a new experiment. And if I'm going to click on it, I will see that the experiment is still running. And if I'm going to click to go inside this experiment, I will see all the different parameters and metrics that were logged by MLflow. And I will be able to see the validation and test metrics in a graph. And this is very cool and useful. And now, please see the number of epochs that are logged here. And if I'm going to go ahead and refresh this page, I will see that new epochs were logged to the database. And I can understand that as the process or as the training is still running, I will see the updates on the experiment tracking tab. And not just me. Everyone who is collaborating with me on this project will have access to this information and to all of those logs. And as simple as that, as fast as that, we created our very first MLflow experiment on DagsHub. Before I'm going to start the DVC interactive part, I will note that if you want to learn how to use Git and DVC at a high level, I added a link in the description below to the DVC in a nutshell video that explains exactly that in less than 10 minutes. So moving to the interactive part, where we will learn how to initialize DVC on our local machine, set a remote storage and configure it with our machine, track files using DVC, and push it to our DagsHub storage. For this session, you don't need to set up anything except having pip and git installed on your local machine. You can find the link to a Notion page with all of the commands that I'm going to use here in the video description below. I'll start by creating a new repository on DagsHub and name it DVC demo, and I will add a Python git ignore file to the repository. Behind the scenes, DagsHub configures a DVC storage with 10 GB of free space and generates the command that will help us to set them up. If I'm going to click on the remote button under the DVC remote in the question mark, I will have all the commands that I will need to set it up with my local machine. I'll start by cloning the Git server to my local machine. To do so, I will copy the Git server URL and move to my terminal on my local machine. I'll change directory to where I want to clone the DagsHub repo to and use the git clone command to clone it. Next, I'm going to create a virtual environment for this project, which I highly recommend using, but you can also install DVC on your Python interpreter. So next, I'm going to run pip install DVC to install it. And now what I want to do, I want to initialize DVC in my local repository. I'll do it by running the DVC init. This command created a .dvc folder, which is a hidden folder, that holds all the DVC's configuration file and a .dvc ignore file that acts as a git ignore. Because of their small size, I will use git to track them. Now we can version our file using DVC locally, but we can't push them to a remote storage because none was defined. To do so, we will need to configure our local machine with the DagsHub remote storage. Luckily for us, DagsHub generated all the commands we need to do so. I'll go back to the repository, click on the remote button, then click on the question mark under the DVC remote, click on the copy button and paste it to my terminal. And before we're going to dive into each of the commands and what they stand for, I'll say that DVC has two different configuration files. One is the local config, which is for local configuration, which is this file is in the git ignore tracking list and will not be pushed to a remote. And the other one is the global configuration that will be tracked by Git and pushed to our Git remote server. All the configuration that are relevant to the user settings, such as the username, the password, or any other configuration, will be set on the local config file and will not be pushed to a remote file because we don't want to overwrite other configuration that our collaborators have. So let's say that I'm collaborating with a friend of mine. I don't want to push my username and password to the remote. First, I don't want it to be visualized to anyone. And secondly, I don't want my colleague to pull it to his local machine and overwrite his configurations. So now let's see what those commands are doing. So the first command is for adding a new remote, giving it a name, origin, and setting its URL. The last three commands are the user configuration, and it will be set only locally on the local configuration file. By running those commands, I've edited the config file, and now by running the git status, I will see that those files were really changed. I will use git to track them and push them to DagsHub. Now I'm going to create a new file named dvcdemo.txt. Let's assume that this is a very, very large file and we don't want to use Git to track it because of its size. Therefore, we're going to use DVC to version it. To do so, I will add it to DVC Tracking. And by doing that, DVC will create a new pointer file and add it to the git ignore file. It will add the original file to the git ignore file so that Git will not track it. We want to track each of our files with only one tool. And it's kind of, and DVC is kind enough to let us know what were the modifications that he did and which file should be tracked by Git. So now let's see those new files and what they contain. So if I'm going to go to the git ignore file, I can see that the dvc demo.txt file was added to the git ignore. And I can see that the dvc.txt.dvc, which is the pointer file, points to the version of the original file and hold metadata about it. If I'm going to see the content, I can see that I has the name, the MD5 hash of the version, and its size. Next, I will use Git to track those two files because they are very small files by running the git add and the git commit. Now, are you ready to the most exciting part of this session? Pushing the file to a remote storage and see it on the DagsHub repository. So I'm going to start by pushing it to the DVC remote, and I'm going to run DVC push, and I'm going to name the origin that I want to push the files to. So -r origin. And if I'm going to go back to my DagsHub repository to see the new state, I will see that nothing was changed. Well, this is okay. This is working okay, and there is no issue. This is because DagsHub is using the pointer files that are being tracked by Git to parse the storage and present the relevant versions of the DVC tracked files. Therefore, to see the data files, we need to also push the Git track files with the pointer files to DagsHub in order to see the DVC demo text file in a repo. So next, what I will have to do is use Git to push all the pointer files. And I'm going to run the Git push from my terminal. And now if I'm going to go back to my repo, I will see both Git and DVC files. Great success. So basically now we can see the DVC tracked file, which is the DVC demo.txt file. It is being hosted on a remote DVC storage. However, all the other files here, the pointer files, the git ignore file, are being tracked by Git and are being hosted on a remote Git server. And as simple as that, in less than, 3 or 4 minutes, we managed to create a new repository, generate a new DVC storage, configure it with our local machine, track a new file using both the Git and DVC, and push it to our remotes. As simple as that, and very powerful for us as data scientists. By that, the DagsHub interactive walkthrough is officially over. I hope you find it helpful, and if you have any questions regarding what I covered in this session today, or you want me to cover more topics in the next ones, feel free to reach out on our Discord channel. You have a link in the description below, or leave a comment to this video and I'll make sure to answer. I hope you enjoyed it and it was helpful, and until the next session, Dags out.